Since we do not get too many classes as our session is fully online, we need to really speed up the lectures, and we have to cover as much as possible in the coming weeks. So in the previous lecture we solved a few problems in the section in first module, which deals with friction. Now in this in today's class we are going to start the second module, and the first topic that we are going to deal with is called truss. So what is a truss? You have seen trusses in many places. This is very truss is a very common engineering structure. An example is given here. This is basically a roof that is supported by 4 pillars, and you can see that you have these bars which are connected to each other. And the support structure that you obtain by connecting such members, linear members, is called a truss. So that's not the that's not a full definition, but to begin with we can say so. So here if you take a section of it, you can see that if you try to draw free body diagram of this part of the truss, we would get something like this. So the load from the roof is being applied on these joints, and at these two joints you have the support, the pillars. So there is going to be normal force from these pillars also. So when we analyze these engineering structures can be very complicated, very difficult to analyze, and it may not fall into simple definitions that we talk about here. But just to begin with, to start understanding these engineering structures better, we will try to first have a very simple definition, and let's understand more about the mechanics of trusses. So you have understood the basic idea. You have many bar members which are connected to each other, and this structure is usually used to support loads in different contexts. Here you can see another truss here. This is essentially a bridge. So this, if you see the skeleton of the bridge, you can see that these are made by connecting different members. And when vehicle is passing through the bridge, loads will be there on the bridge. So it won't be on the joints, but when these some sort of the support system through which vehicles are passing are usually connected to the joints. That may not be the case all the time, but let's just say that is the case. If that is the case, loads will be there on the joints. And of course these two this bridge is supported at the either ends. That means you have these support reactions from this which are an external force. Now so to begin with, we are going to use some assumptions. So assumption number 1 is that loads are always applied on the joints. So the second assumption is that all joints are connecting members are pin joints. So what does this mean? So we usually a simple truss can be obtained by connecting 3 simple members. These are simple 3 members, and these 3 members are connected at these joints. So pin join means if you disconnect these members from all other joints except this joint, you can rotate each member independently about the pin joint. That means that you will be able to rotate these members freely about pin joints if there are no if there are no other members. So you essentially have some sort of some sort of mechanism to make sure that without friction you are able to rotate all these members without causing any friction. So that is an assumption that we will make for the trusses. So what does that imply? How is it important for us when we analyze the external forces on the members? We will discuss those things. Now this truss should be supported somewhere, right? Let's say this is supported here. So this is also a pin joint. All joints are pin joints for trusses. And this here is a fixed support. Means it's fully fixed. It's like fixing it on a wall. But this joint is pin joint. Means you can freely rotate these members about this joint. Another kind of support is a roller support. Roller support means it's like having wheels on the support. So this is a roller support. So from the roller support you can only have support reaction normal to the surface. You cannot have forces which are parallel to the surface. Why is it not possible? Because even if you have such a force, these rollers will slide in the plane and will make sure that there is no net force. So from the roller support you can only have a normal force. From the fixed support you can have force in any arbitrary direction. So force can act in any arbitrary direction. That means force in an arbitrary direction can be resolved into two components. A vertical component, if F is the Fs is the support, you can have an X component and a Y component. Y component and an X component. And you know that if this angle here is theta, and you know that a cosine and sine relationship is there to resolve Fx. So that is the kind of reactions you can have from a fixed support. Now, because of these assumptions which we make for a truss, so when we use the technical term truss, you should automatically understand that these assumptions are applied. Loads are always applied on the joints. All joints connecting members are pin joints. Now if we consider a member, let's say this is member AB. You can what kind of forces can you have? See, either ends are all joints are pin joints, right? If this member is connected to a truss, these two joints should be pin joints. If they are pin joints, this member will not be able to sustain any torque. Right? If both ends are freely able to rotate, then it cannot take any torque. There cannot be a moment on this bar. So there can only be forces. What kind of forces? Let's say there is a force here and here. Is this possible? This is not actually possible, because when you have such external forces on this member, that means that there is a net moment. If you take moment about this point, you can see that there is a net moment about A or any point. So this is not possible. So what is possible? So what is possible? Only two types of forces are possible. In each members of the truss, you can either have tensile force or compressive force. You can either pull these bars away from the center, or push from either side, means compress it from both sides. These are the only forces possible. So this will make sure that there is no net torque. So if you take torque about any point, these are equal and opposite, obviously. So if this is F1, this is also F1, this is F2, this is also F2. Equal in magnitude, opposite in direction. So they will get cancelled out and there will be no net torque. So this is the result of this assumption. Now I think I've given enough introduction for you. You know most of the basic laws in mechanics, so we will not spend a lot of time describing basic definitions. Let's go ahead and try to solve a problem. We have a very simple truss here. So this one is a fixed support. You can see that it's fixed here, and this is a roller support. You have the dimensions are given here. This is 2 meter, this is 2 meter, and you have an external force 500 Newton here. This angle is 45 degree. So the all parameters, this structure is like fully defined, all dimensions are given, and there is only one external force, it's 500 Newton. Of course support reactions are there, they are also external forces. Now we would like to find out what are the forces developed in each members due to these external forces. Why do we need to do that? So if you are designing a bridge, assume that all of these members are connected using pin joints. Like I told, for a bridge, that doesn't need to be the case, but let's say that is the case. If that is the case, what will be the forces developed in each of the members? Let's say huge trucks, 10 trucks are passing in the bridge, and there is a limit up to which each members can sustain a force. You know that if you have a bar, you have a steel bar, right? So depending on the material properties of the steel, how much force can you apply on it? How much tensile force or how much compressive force? So if you apply tensile force beyond a limit, this is going to actually fail, right? If the force is too high, and if compressive force is too high, again the member can fail. It can bend, it can break, we don't know. So this is the member can fail. So to avoid failure, we would like to see, we would like to make sure that the forces that is withstood by this structure is distributed between these members in such a way that the members are able to withstand the total load. So we know the material properties of the steel, we know the Young's modulus and everything. Young's modulus is not enough. The fracture criterions, how much the failure criterions of the steel, let's say assume we already know, so we can actually calculate the maximum load which it can withstand, and we will design the bridge in such a way that each members, the force in each members are not beyond the tolerable magnitude. So that can be one objective. So to analyze, let's analyze this simple structure in that way. We would like to find out all support reactions and member forces, and we will using the concepts we have already studied about the truss. We will try to solve this problem using a method called method of joins. In method of joins, we will consider each joint at a time, and we'll try to draw the free body diagram of it, and we'll try to find out each member forces. So let's take out each joints. Let's take out this joint B. You have external force 500 Newton here, and you have two other members which are connected to this joint, and I've already told you that a member can have only tensile or compressive forces. So the direction of forces direction of force in the member will always be parallel to that of the orientation of the member. So from the member CB, you can only have forces in this direction, right? You can have forces only in this direction. This direction means this direction of BC. It can be compressive or tensile. So it can be in this direction or this direction. So that doesn't really matter, because when we try to solve the problem, we can simply assume the direction of each members. Let's say you have tensile force here. If you have tensile force here, this will be the direction of FBC. FBC is the member force in BC. FBC is the member force in BC. Now why did I use this direction? BC is parallel to this BC first. Secondly, I simply assumed that you have tensile force here. That's why force on this joint is in this direction. So what is a tensile force? If this is BC, tensile force means tensile force is the kind of force you have on a rope. So it's away from the joint. It's always away from the joint. So on BC you have in this direction. So in the joint, this should be opposite, away from this joint. I hope you have understood what I've just said. So tensile means, always think about the rope. If there is a rope connected to this joint, let's say BC is not a member, BC is simply a rope. So a rope will always try to have forces away from the joint. You cannot push towards the joint with a rope, because rope cannot withstand compression. So here also you assume that in BA also you have tensile force, so FBA. Now this angle, this is 45, and that means this is also 45. Now let's consider next joint A. So at joint A you have FAB. Again we've simply assumed if AB and B are the same thing. Okay, we have simply assumed tensile force. Here also we have assumed tensile force. This is FAC, right? FAC. And from the support, what kind of forces you can have? Forces, this is fixed, so you can have force in arbitrary direction. So a force in an arbitrary direction can be resolved into two parts, X component and Y component, horizontal component and vertical component. So let's just say it's a horizontal component is RAX and vertical component is RAY. There we go. Now consider next joint C. You have F BC, F AC here, and this angle is given here, which is 45 degree. Now this is a roller support. So remember, for roller support you cannot have forces which are parallel to the surface on which it rolls. You can only have normal forces. So I can this roller is not, you can't really lift it from here. Okay, that's actually fine. You can assume a direction, means let's here say this is upward, this is RC, because this is a normal force. There is no support reaction in the horizontal direction. Now so we have joint B, A and C. We would like to find out everything, right? All member forces FAB, we would like to find out FAB, FBC, FAC, and at A horizontal component, vertical component, and support at C, which is just a vertical component. Not vertical component, it's a vertical force. There is no horizontal component. So how many unknowns do we have? 3 plus 3, 6 unknowns. How many equations do we have here? Net force in X direction should be 0, net force in Y direction should be 0. Each of these should be in equilibrium, right? This is not moving. So 2 equations here, 2 equations here, 2 equations here. Total 6 equations and 6 unknowns, right? 6 equations, 6 unknowns. So this is a this linear system can be solved. Now it's straightforward. Since this is the first problem, I'll just talk a little more about it. So you can write down all the 6 equations. and find out the unknowns. So for practical purposes, we will look for some features and characteristics to make our problem solving easier, especially for exams. Here you have 4 unknowns. For this system you have 4 unknowns. Here you have 1, 2, 3 unknowns. Here you have 1 and 2 unknowns. So where will you start? It's a good idea to start with this system. You can actually start with anything and write down all equations and solve the system. 6 equations and 6 unknown means it's a linear system that is perfectly solvable, no problem. But for practical purposes, it's a good idea to start with a system which has least number of unknowns and find out the unknowns and supply the unknowns in the next system. That would be kind of easy, right? So to start with, take this system. Here for B, net force in x direction should be 0. That means that $500 is a force in x direction, fully in x direction. It's towards right, so it is positive. Next you have a component FBC, a component of FBC, horizontal component of FBC. So this angle is 45, so FBC cos 45 plus FBC cos 45 equal to 0. FBC cos 45 is equal to 0. Now net force in y direction should be 0. So that means that what are the forces in y direction? FBA is there. Is it positive or negative? That is negative because it is acting downwards. And you have a component of FBC cos 45, that is the component in vertical direction. It's again downwards, negative, so equal to 0. So in the first equation, FBC is the only unknown. You can calculate FBC. You can calculate FBC. So FBC is done. So if you substitute FBC here, you will get FAB, which is done. FAB and FBA are the same thing, okay? And many problems with regards to direction will be sorted out here. You can see that you only have components towards right here. That cannot be the case if it is in equilibrium. So FBC will be negative. So FBC negative means we assumed tension in FBC. That assumption is wrong. It's actually you have compressive force. So if this is positive, so if the resultant is the calculated value is positive, we will say our assumption is correct. Means you have tensile force in BC, okay. If answer is negative, we will say that our assumption that we have tensile force in the members is wrong. Our assumption is wrong. Hence it must be compressive forces. Now let's move to, so now we know FBA and FBC. So FAB is equal to FBA, and if you use FAB here, again you have 3 unknowns. So let's not solve this here, let's solve this one. So here FBC is known, right? So for C, net force in x direction should be 0. That means that FAC is towards the left, so that's negative, and FBC, a component of FBC, cos 45, that is also negative because it's towards right. Net force in y direction should be 0. That means that RC, that is positive because it's upwards, plus FBC cos 45, right, a component of cos component of FBC, that is also positive because it's again upwards. So that is 0. Now we have already calculated the value of FBC, right? FBC is already calculated. So substituting FBC here, we'll get FAC, and if that is positive, we'll say it's tensile, and if that's negative, we'll say our assumption was wrong and it's compressive. And once you know about FAC and FBC, again you only need FBC here. Substitute FBC here and you'll calculate RC. If RC is positive, let's say we will say that our assumed assumption of support, here in this case you can only assume upward reaction because it's this is drawn like you cannot lift it. I mean, if there is a force in this direction upwards, this is going to be lifted, so that's such a reaction is not possible. So there should be an upward. Anyway, that's something I'll get it from here, but you can take an upward or downward direction and get the correct answer, no issue. So RC, if RC is positive, RC will be positive, so it's assumed direction is correct. If you have taken RC downwards, you will get it as negative, and so you can correct the direction here, or you can simply say that you can simply write down negative values for reaction, which simply means that direction is opposite. So you have now we go to the last junction A. Here FAB and FAC we have already calculated. So RAX and RAY are the only unknowns. That's going to be easy. Net force in x direction is 0. That means that minus RAX plus FAC is equal to 0. Means FAC is equal to RAX. Net force in y direction is 0. That means that FAB minus RAY is equal to 0, which essentially means FAB is equal to RAY. So FAC and FAB are already calculated, and you will get values of RAX. And if you would like to find out the resultant of support reaction, you can calculate it. If it is specifically asked in a question, you can calculate it. RAX and RAY are the horizontal and vertical component of support reaction, if uh, if you'd like to calculate the magnitude of total support reaction, that will be Rax square plus Ray square square root. And if you'd like to find out the direction, you can use the tan inverse equation. Depending on the direction of Rx and Ray, it will change. That is something you are familiar with. If you have the components, you can find out the magnitude and direction of resultant. That's something you are familiar with, so I will not spend time on it. So we have completely solved the problem. And let's I'll just talk about one more problem, and I'll not spend as much time as I have spent for the previous problem. So you have another truss here you have roller support, here you have fixed support. Both are, of course, all joints are pinned. Consider if you are using method of joints, which is the only technique we have studied so far. What do? Take out each joints, see you have FBC here. Of course, we'll simply assume, let's say you can assume tension or compression, but just let's say I'm assuming tension in all members. So this is FBC and you have FCD. Okay, in the previous problem, if there is any mistake, please do let me know. Maybe in the direction or some cosine components or somewhere, if I've made any mistake, do let me know. So FBC and FCD. So these are the member forces. Now support reaction, this is a fixed support, so there will be the direction of support reaction will be arbitrary, so we will use a we will simply assume the we will take RCY and RCX as the vertical and horizontal components of the support reaction. So there we have 4 unknowns. Now consider joint B. You have FBA, FBD and FBC. You also have an external force which is 400 Newton downwards. And what are these angles? That is something you can find out from here. So this is 3 meter, this is 3 meter, and this is 4 meter. So this will be 5 meter, and this angle will be tan inverse 3/4. You can calculate it, right? If this is theta, tan theta will be equal to tan theta will be equal to 3 divided by 4. So theta will be equal to tan inverse 3/4. So you can calculate it, and you can put it here and here. So there we have 3 unknowns, and here you have another. So this is B and this one is C. Consider join A. You have F AB, F AD, tensile force from member AB, tensile force from member AD, and this angle, what is this angle? If this is theta, this will be 90 minus theta, right? Again, that's you can easily find it out from the geometry. You know, theta, this is also theta, this is 90 minus theta. So you know that. Let's call it alpha. And you'll have a one reaction force. This is a roller support, this is not a fixed support, which means you can only have normal reaction, and we will call it RA, reaction at A. And consider join D. You have F CD, F BD, and F AD. This angle is again alpha, right? This angle will be again 90 minus alpha, which is theta. If this is theta, this will also be theta. Now how many unknowns are there? 1 2 3 4 5 6 7 8 unknowns, and you have 4 systems. Each system will have 2 equations. Sigma fx is equal to 0 and sigma fy is equal to 0. So from 4 systems we have 8 equations, 8 unknowns and 8 equations. You can solve the linear algebraic system. So in any order you can solve it, but for practical purposes, for an exam, it's a good idea to start with the system which has low number of unknowns. Here, is there any system with 2 unknowns? There is no system with 2 unknowns, so this is going to be a little difficult, not very difficult. So the count we did in the beginning, 8 equations, 8 unknowns. So we can definitely solve the system. Now how do we solve it? Is something we can work on. So is there any, so if you want me to suggest a starting point, so I'm just here I'm trying to count I'm trying to consider two systems together so that you can solve it. If these two together will have how many unknowns? These two together will have this one and this one together will have 1, 2, 3, 4, 5 unknowns. If you consider this and this, you have 1, 2, 3, 4, 5 unknowns. Here F, B, C, C, D, again 2 extra unknowns. Okay, even if you combine two systems, I don't think you have a system with 4 unknowns, 2 combined. Okay, I forgot one, this one here. There is an external force 600 Newton here, right? I forgot to do that. So this 600 Newton I forgot to mark it here. Now I've marked. So here you can see that unlike the previous problem, in the previous problem we could start with single equation and go ahead and solve all systems. Here you can't do that because there are too many unknowns. So what you need to do here is that not only here, for all problems, first start by finding all support reactions. Consider the structure together as a single system and write down the equilibrium equations for the whole structure, and using that you find out all support reactions and substitute the support reactions in these equations to find out all other member forces. So using that way it will be easier for you to deal with the problem. Otherwise also you can solve the system. You have 8 equations and 8 unknowns, but it's going to be a little difficult, right? So here, so what is the strategy? Consider the structure or I'll write here, there's no space here. Okay, draw free body diagram of the whole structure, right? the whole truss. So you have 400 Newton here, 600 Newton here, and here you have RCX, and upward you have RCY, and here you have RA. So consider the equilibrium of this whole thing. So how many unknowns do we have here? 1, 2, 3. 3 unknowns. And how many equations do we have? Sigma fx is equal to 0, sigma fy is equal to 0. One more equations we have here, because this is a full 2D system. You can also have the moment equation. For the single joints we could not come up with moment equation, but for this whole truss you also have the moment equation. Net moment about any point is 0. 3 equations and 3 unknowns. So you can find out RA, RC, Y and RCX. So once you have that, you can substitute it here, RCX, RCY and RA. Now you have a much simpler problem. So how many unknowns do you have? 1, 2, 3, 4, 5 unknowns remaining, for which you have more than enough equations. You can, if you know RA, you can solve for FAB and FAD. If you know RCY and RCX, you can solve for FBC and FCD. If FCD is known, here only 2 unknowns are remaining, which can be calculated. So FAB is known from here, FBD is known from here, so only FBC is remaining, which you can calculate. So all of those can be calculated. So this is the procedure. Remember, in the previous case we started solving joint by joint and found out all the unknowns, and here we found out that when we solve joint by joint, you can solve the problem, but it's a little difficult. So it's a good idea to start by finding out the support reaction. So always remember this step. Start with support reactions. Draw the free body diagram of the whole truss, find out the support reactions. So here what will be those equations? So sigma fx is equal to 0 means net force in x direction is 0. So RCX plus 600 is equal to 0. So RCX is equal to minus 600. Simple. Now net force in y direction is 0. That means RA plus 400 Newton is downwards, fully downwards, so minus 400. RCY is upwards, so plus RCY equal to 0. Now moment about which will you take? There are 1, 2, 3, 3 unknowns here. 2 unknowns are passing through C. since the most number of unknowns are passing through C, we will take moment about C. To make things easier, you can take moment about any point, but to make things easier, it's a good idea to take moment about C, which should be 0. So if moment about C is 0, here, so R, that means that R moment about, you have to consider all external forces, right? RCY and RCX are passing through C. So RCY into 0. The perpendicular distance between line of action of RCY and point C is 0. So RCY multiplied by 0. And RCX is also passing through C. So RCX multiplied by line of the distance between line of action of RCX and point C is 0. So RCX multiplied by 0, that is also gone. Now RA multiplied by, what is the perpendicular distance between line of action of RA and point C? RA is, this is the line of action of RA, right? What is the perpendicular distance between line of action of RA and point C? That will be 3 plus 3, 6. So RA into 6. So that is in C. About C, RA is trying to rotate the whole structure about C in clockwise direction. So we will take as negative. So clockwise direction moment is negative. Now consider the 400 Newton force. The 400 Newton force is acting at B. So the moment due to 400 Newton force will be 400 multiplied by distance between line of action of 400 Newton and point C, and that distance is 3 meter. 400 multiplied by 3, and that is about C. It tends to rotate the structure in anti-clockwise direction, so we will take it as positive. And 600 Newton, you have 600 Newton external force, next external force. So you have total of 1, 2, 3, 4, 5 external, 1, 2, 3, 4, 5 external forces. You have to consider all external forces. You don't need to consider internal forces, remember. So 600 multiplied by, what is the distance between line of action of 600 and point C? That is 4 meter. So about C, the 600 Newton force is trying to rotate the structure in anti-clockwise direction. So anti-clockwise moment means positive, so equal to 0. So from here you can calculate RA. Once you have RA, you can calculate RC by RCX, you already know. So this is known, this is known. FBC and FCD can be calculated. RA is known, FAB and FAD can be calculated. Once these are known, you have minimal, small number of unknowns in other equations which you can calculate very easily. So remember the step. First step, take the truss system as a whole and find support reactions. Second step, find member forces. And if you get negative values for these member forces, you will say that assumed direction, which in this case is tension everywhere, We'll say that if it's negative, that assumption is wrong and you have compressive force in the member. So if value is positive, you say that assumption is right and you actually have tensile forces in the members. So that's how we deal with this problem. So this lecture is longer than I thought, I think, but anyway. Okay. We'll just talk about one more type of members. So when you solve the system, this is another truss. So just like the previous problems, you can solve the system if these are given. If P is given, you'll consider the whole. We'll consider the equilibrium condition of the whole truss, and you'll find out the support reactions. After that, you solve joint by joint and you'll find out all member forces. But here, if you do that, and you will see that many member forces are 0. Here P is the external force. Irrespective of the value of P, let's consider joint A. For joint A, you have FAB in this direction and you have FAF here, right? Member force in FAF and member force in AB. Any other forces? No external forces. This is it. So here sigma Fx is equal to 0, net force in x direction should be 0, which means that FAB is equal to 0. Net force in y direction is equal to 0. That means that F force in AF is also 0. So this is interesting, right? Without solving the entire problem, without knowing the unknown force on the member, you have figured out that member force in AF and FAB are 0. Is there any more members which will have 0 force? D. Consider D. F ED. Here you have FDC, and that's it. No other forces. So whatever the value of theta is, you will okay, let's solve the system, right? Sigma Fx, net force in x direction should be 0. So FED sine theta should be 0, which means FED is 0. Sigma Fy, net force in y direction is 0. That means minus FDC minus FED cos theta is 0. So FED is already 0. This term is 0, which means FDC is also 0. So how do we find out this member, 0 force members? So AF has 0 force, AB has 0 force, ED has 0 force, DC has 0 force. And by this time you must have guessed. How do you find it out? At a joint, if you have only 2 member forces and no other external forces, and in that case both members will have 0 force. Here also you have a joint, you don't have any external force, only 2 members, so those 2 members will have zero force. But you don't have such cases here. You have two joints here, but you have external forces on those joints. Here you have one joint and you have external force. So even if you don't have any external force here, still you have three members. So it's possible to balance out different forces between members, and you can have non-zero member forces. But if you have only two members connected to a joint and there are no other external forces, means these two members are going to be zero force members. So you can by simply looking at the problem, you can remove these four members. Not remove, you already know that you have zero force in these four members, and you can easily solve the problem. So in real life, for engineering structures, such as zero force members are not useless. They are sometimes used to make sure that your structure is safe enough. If some other member fails, or in certain cases these zero force members will have to play a role, will have to take a load if there is any unsuitable condition, there is any failure, or some extra forces comes out here in a certain situation or something like that. So the zero force members are used in such cases. So you know how to recognize these members now. Two members, no other external force, there will be zero force members. So now you can easily calculate other member forces. So here also, see at E you don't have any external force, but you have four members connected to E. So these members may not have zero force. It can have certain force. Only if there is two members and no other external force, you can assume that it's a zero force member. Okay, that's it. I'll stop here.